Welcome to Lecture 43, in which we're going to remember what we intentionally forgot in the previous two lectures, and that's the fact that light consists of waves. Remember that we were able to use the ray approximation, the approximation of geometrical optics, when the systems we were concerned with, our lenses, our mirrors, things like that, were large compared with the wavelength of the light. Physical optics, as it's called, as opposed to geometrical optics or ray optics, becomes important when light interacts with systems that are the size of the wavelength. And we're going to have many, many uses for light as a wave in technology, in very precise measurements, in observations we may make, astronomical observations, and so on. But we're also going to find out that the wave nature of light fundamentally limits our ability to image, particularly either small objects or distant objects that are very close together. The fundamental phenomenon that waves do that matter does not do is the phenomenon of interference. And it's interference that we're going to be dealing with when we talk about physical optics, about the wave aspects of light and how they affect optical phenomena. So let me remind you a little bit about interference, which is a subject I first introduced back in Lecture 18 when I was talking about waves. In fact, we will see a number of connections here with Lecture 18 because we're talking once again about waves, but now specifically about light waves. So let me remind you that interference can be either constructive, which it is when wave crests meet each other and wave troughs meet each other. So here we see two waves. They happen to be out of step with each other, but they're out of step by a full wavelength, lambda, again that symbol for wavelength, and crests meet crests and troughs meet troughs. And since two waves can exist at the same place at the same time, and simply add when that happens, this wave will be twice as big as either of the two waves that is making it up, either of these two interfering waves. That's constructive interference. Destructive interference occurs when crests meet troughs. So here's an example of destructive interference. Here are two identical waves, except that now one is half a wavelength behind the other, half a wavelength instead of a full wavelength, and that causes the crests to line up with troughs and the troughs to line up with crests, and those two waves cancel out completely. That's complete destructive interference. So how would we make these kinds of interference happen? Well, if we had two waves, we took some light, for example, and we split it, and we let one light wave travel a full wavelength longer than the other one, when they came back together and we rejoined them, they would be constructively interfering, and we'd get back the original light. If we let them go on different paths and one of them came back half a wavelength after the other, or before the other, then the two waves would completely cancel and we would see no light. And of course, there's all kinds of possibilities in between. But the big ideas are constructive interference and destructive interference, and then a continuum in between. Here's an example of interference of this sort. It's interference in thin films, and you've all seen this. If you look at a spill of oil, say on a wet road, you see beautiful shimmering patterns. Not so good for the road, not so good for the environment, but it's beautiful. You see these shimmering patterns. If you take a soap film, as shown here in the photograph, and you hold it up to light, you will see these shimmering patterns of different colors. What's causing this? Well, as you can see in the diagram on the left, what's happening is light is coming into this thin film of material, and if the thin film has a thickness such that light traveling through the thin film comes back and is interfering with the light coming in at the surface, and those two waves are in step, then I'll get a bright region looking in at some particular angle or at some particular wavelength. If those two waves come back and interfere destructively, then I will see darkness at a particular wavelength or a particular angle. And the reason I'm seeing multiple rainbow colors here is the criteria in that thin film of soap bubble for constructive and destructive interference are different for different wavelengths. So I see those beautiful shimmering patterns. You'll notice it goes completely dark at the top. At the top, there is no visible wavelength. It's very thin at the top. A soap film tends to drain down from the top, so it's thicker at the bottom. At the top, there is no visible wavelength that can undergo constructive interference in that film. And the constructive interference condition is when twice the thickness, because the light is going back and forth, is m plus a half lambda, where m is an integer. And you might say, why is it m plus a half? And the reason is because the light undergoes a phase change at one boundary, at the first boundary, when it's going from air to, say, glass or soap film or whatever this thin film is made of. But it does not undergo a phase change at the other boundary at the far side. And so what's happening is the light that reflects off the front surface and the light that reflects off the back surface are interfering, And the condition that that interference be constructive is when twice the distance is m plus a half lambda, and I've marked that lambda n because I'm talking there about the wavelength in the particular material we're talking about, which is different from the wavelength in, say, air, because the refractive index will be different. So there's a common example interference in thin films, and this phenomenon can be put to lots of good uses. In particular, it's used for very precise optical measurements of very, very small distances. You use this method called interferometry. You're looking at interference patterns to infer distances. A more common kind of interference, or one that we're going to deal with quite a bit in this course, not only now but also later when we get into quantum physics, is the interference that Thomas Young used in 1801 to prove definitively that light consists of waves, a definitive result that held at least until 1905 when it became questioned again. But light definitely has wave aspects, and Young proved that using two-source interference, which is something we talked about in Lecture 18, and I want to modify that a little bit now and talk about it for light. So let's go to our big screen, and let's talk about two-source interference. So here I have two sources of light, and I have to assume they're coherent. That is, they are emitting light waves in exactly the same phase of exactly the same frequency. We could have done this for sound waves with two loud speakers being driven from the same source. We could have done it with water waves if we had a couple of things bobbing up and down into water in synchronism like this. It's a little bit harder to make two-source interference with light, but if we did have two light sources, what would happen is they would send out circular wavefronts or spherical wavefronts in 3 dimensions, and those wavefronts would go on out. And as you can see here, there are places where wave crests cross, wave crests cross, wave troughs are crossing there, wave crests, wave troughs. That's a region where the waves are interfering constructively. In between, right there, is a place where a wave crest is crossing a trough. And as the waves propagate outward, nevertheless, we still have these same regions, these bands, these lines in which we have constructive and destructive interference. Well, let's notice those lines. There they are. Those are the lines of constructive interference. You have bigger waves heading out along those lines. In between, there are regions where the waves almost, not quite, but almost, cancel each other out. That's two-source interference. If we were to put a screen up here, we would get regions of bright and dark alternating on that screen. Bright, 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 and in between dark, 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 dark. Now that's two-source interference. But how do you get two sources of light? Well, ultimately you do what Young did, and you do what everybody who's done this experiment since has done. Instead of trying to make two coherent sources of light, you instead put a single source of light through two small holes, slits. And so we talk about slit systems, and we talk in this case about two-slit interference. So instead of having two-source interference, I now have two-slit interference. Here's some kind of barrier to the incoming waves. Waves go through the two slits in the barrier. Each slit acts as a new source of circular waves for reasons we'll talk about later, and we get exactly the same interference pattern. Let me leave that interference pattern on the screen for a minute as I show you that this actually does occur. So let's go over and look at our demonstration on the table, and we'll see that we are in fact seeing two-slit interference. So what I have here is a rather small, fairly modest semiconductor diode-based laser giving out red light. I have a system here which has a number of different slits and other small apertures for light to go through, and I have it set to a slit whose spacing between the two slits is 0.25 millimeters, a quarter of a millimeter. And then I have some distance out to a screen, and this is the classic experiment that shows that light is a wave, because if I look on that screen, what I in fact see on the screen is a pattern of light, dark, light, dark, light, dark, light, dark, light, dark. And if we could darken the room, you would see quite a few of those light, dark bands. But what I'm seeing here are about 5 of them. In fact, just what I have on the big monitor. So we're seeing the first 5 bands of the interference pattern. There's a central band in the middle, and then we're seeing these other bands. And that is an indication that the light waves passing through the two slits are interfering and producing, when they get to that screen, that interference pattern. They're producing the interference pattern all along, but I just put the screen there to intersect them, and so we could observe that pattern. So that is double slit interference, and we're going to go a little further with double slit interference than simply to use it to demonstrate the wave nature of light. We're actually going to do some calculations with it. In fact, we're actually going to come back here in a minute, and we're going to measure a very tiny quantity namely the wavelength of light. So let's go do that. Before we can measure it, we've got to figure out a little bit here what's going on. So let's take a closer look at two-slit interference. So here's a picture of my two-slit system before I had the slits this way. Now I've got them vertically. The slit spacing I'm going to call D. That was the 1/4 of a millimeter over there. I'm going to have a screen some distance L away. So that's the distance between the slits and the screen in my experiment. And I'm going to notice that there are paths from one slit to some point P on the screen, some arbitrary point P on the screen. That point P is a distance y away from the center line between the two slits. And I want to know where the bright and dark fringes of that interference pattern, they're called fringes, are as a function of this distance y. And here's the deal. From the lower slit, it's a distance r2 to point P. From the upper slit, it's a distance r1. Now this L is typically big. In my case, it's a meter, 1,000 millimeters. This D is typically small. In my case, it's a 1/4 of a millimeter. And consequently, you might say, well, these distances are basically the same. Almost. Very close. I couldn't measure the difference with a meter stick. But the interference of light can measure it because the interference of light is sensitive to distances that are as small as about the wavelength of light. So let's blow this thing up and take a little look at it. The path difference here has to be a multiple of the wavelength if I'm going to have constructive interference. And the paths are not quite the same. So here we go. Blow it up. Here's that slit separation D. Here are these two lines going way out to point P, which in this blow up is way far away. These lines are almost parallel, so close I can sort of assume they're parallel, but they aren't quite parallel. And notice what's different. This path is a little shorter, and it's shorter by this distance. And this distance by trigonometry is this piece of the triangle, which is the hypotenuse, and its length is D, the slit separation, times the sine of this angle theta. And the angle theta is the same as the angle toward that point P. And you might say, which angle? The angle of the lower ray, the angle of the upper ray. Well, those are truly almost exactly the same, so we can ignore that difference. So this is the path length D sine theta, the path length difference. So this ray from the lower slit to get to this point P, which is above the center line here, has to travel a greater distance, and the greater distance it travels is D sine theta. And we've seen that we get constructive interference if that path length difference is a multiple of the wavelength. So I can write D sine theta has to be m times lambda, where m stands for any integer. Could be 0, it could be 1, it could be 2, it could be whatever, but it's got to be an integer to get maximum constructive interference. Now for small angles theta, and this picture is exaggerated. If you look at my apparatus, the angle to any of those points on the screen from where the slits are is very tiny. For small angles, the measure of angle, theta, in radians, is equal essentially to the sine, and that's equal essentially to the tangent. They're almost exactly equal. That's saying the sine curve has slope 1, where it goes through 0, if you want to get mathematical about it. And the tangent of that angle is y divided by L, because there's the triangle, right triangle formed by either of these pink lines. Y over L is the tangent of that angle. So sine theta is approximately tan theta is y over L. So we're going to have bright fringes when D times y over L is an integer multiple of the wavelength. That tells us what y is. Y is m times lambda L over D. So you calculate the quantity lambda, the wavelength of the light you're using, this L distance to your screen, D the slit separation, and you will see bright fringes at integer multiples of that quantity along the screen, measured from the center line, with one right at the center, which is the m equals 0 line. You'll get destructive interference if the path difference is an odd multiple of the half wavelength, and consequently, you'll get dark fringes when it's y equals m plus a half, lambda L over D. So that's two-slit interference. Let's use two-slit interference to measure the wavelength of visible light. We know there are going to be bright fringes when y is m, lambda L over D. We know there are dark fringes when y is m plus a half, lambda L over D from this diagram. Let's do the numbers. We solve the bright fringe equation for lambda. The first fringe, m equals 1, occurs when lambda equals yd over L. Put m equals 1, lambda equals yd over L. Now we can't do any more numbers till we have some numbers to do, so let me go over to our experiment and get the numbers. Now, this apparatus has a nice built-in scale, and I've put the slits at 10 centimeters and the screen at 110 centimeters, so the difference is 100 centimeters, 1 meter, 1,000 millimeters. It doesn't really matter where the laser is. That doesn't enter our picture. That's just shining light to go through those two slits. The slits are 1/4 of a millimeter apart. That's what I'm told. And now I have to also get Y. Y is the distance between the center fringe and the first fringe. Now I can see 5 fringes on there, and rather than try to measure the tiny distance from the center fringe to the first fringe, I'm going to measure the distance between the second fringe in one direction and the second fringe in the other direction. And that distance will be 4 times the distance from the center to the first fringe. So let me measure that. That is just about a centimeter, a little over. It's between 1 and 1.1 centimeters. I could call it 1.05, but it's hair less. I'm going to call it 1.04 centimeters or 10.4 millimeters. Okay, so 10.4 millimeters, that's 4 times the distance I'm interested in. Divide it in half, I've got 0.26. So that's going to be 2.6 millimeters, 0.26 centimeters, 2.6 millimeters for that separation. So let's go back to our big screen and continue the calculation with those numbers. So we've got 2.6 millimeters for Y. We've got 1/4 of a millimeter for D. I'm doing this all in millimeters. Upstairs comes out millimeters squared. Downstairs millimeters. So the answer is in millimeters. 1,000 millimeters for that 1 meter separation of the screen. 0.00065 millimeters. And if you convert that to nanometers, you get 650 nanometers. And that is indeed just about the color of visible red light. So we have correctly measured the wavelength of light here. That's a small quantity. That's 650 billionths of a meter, a little over 1/2 a millionth of a meter, and we have quite accurately measured it using 2-slit interference. Okay, well, let's move on a little bit and look at what happens if we have more than 2 slits, which we can also do. So what happens if we have more than 2 slits? Well, let's consider a case where we might have 3 slits. Here are 3 slits. If you want a true maximum, all those waves have to arrive in phase at that point on the screen. And so we have the same criterion, that d sine theta, the path length difference, has to be m lambda for all of them. So d is the separation between individual slits. It's got to be true for all the slits. For a minimum, things get more complicated. We have n waves, 3 in this case. We're trying to sum them to 0, and they've got to sort of be staggered in phase to come out 0. So the condition for minimum becomes a little bit more complicated. What happens if we have multiple slits? The criterion is actually d sine theta has to be some integer divided by the total number of slits times lambda, and the integer can't be a multiple of the number of slits, or you'd have constructive interference. This is getting complicated. But let's take a look at what happens. What happens is this. When you have lots of slits, you have this criterion for a maximum, this criterion for a minimum. When this number of slits is relatively small, for example, at the top in this picture, you get the kind of interference pattern we just talked about. But as the number of slits increases, an interesting thing happens. The brightness of the fringes increases, and the fringes get narrower and narrower and narrower and narrower. And if you have very, very many slits, you have very bright and very narrow, precisely defined bright fringes in the interference pattern, and in the in between you have almost nothing. I can demonstrate that with my device over here, which I'll do very quickly by putting in instead some multiple slit systems. So let me do that. I'll start out, as before, with 2 slits. Let me dial this down. And on our screen, we see a rather fuzzy pattern of a few dots. They're a little more widely spaced than before because the spacing of the slit is a little bit different. But there they are. And now I'm going to dial from 2 slits to 3 slits, and you can see the dots have become a little bit brighter. You may also notice they've become a little bit more distinct and a little bit narrower. 4 slits, they've become brighter still and smaller, and the black gaps between them, where there's very little light, have become wider. And finally, 5 slits, I have a series of quite bright dots across there. The number of dots has nothing to do with the number of slits. These patterns were basically the same in all cases, but what's happening is the bright interference fringes are becoming much brighter and much narrower. Now, this is ultimately the principle behind something which is called a diffraction grating. A diffraction grating is a system in which you have many slits, or in other cases, many structures that will reflect light, because this can happen either with reflection or with slit-like systems. And if there are a great many of them, then individual wavelengths will be sent very precisely off at different angles. And you'll see bright regions for different wavelengths at different angles. And this can be used like a prism, but much more accurately to break light up into its colors. When you look at a CD or DVD or Blu-ray disc at the back side, the side that has the information, and you wave it around, you'll often see bands of bright colors. That's because the tracks that carry the successive pieces of information in the CD or DVD or Blu-ray disc are acting as a so-called diffraction grating, which is what this is called, and you're seeing at different angles these intensity maxima for different wavelengths of light. This is the basis of astronomical spectroscopy and spectroscopy used in a lot of other areas of science. Here's an example. This is called a grating spectrometer. It's used to analyze light. And what it does is send light from some source, like from a telescope or whatever, through some kind of entrance slit to collimate it, and then it goes through a grating with typically many thousands, in most cases, of lines. And the way that grating diffracts the light or produces this interference pattern sends different colors to different angular positions on that screen, and that's how you separate the colors and analyze the light for its constituent wavelengths. So that's an example of a multi-slit system. And I use the term diffraction grating there because the terms diffraction and interference are kind of fuzzy terms in their relationship to each other. And I want to end this lecture by talking a little bit about diffraction itself. Diffraction is best understood by a principle called Huygens principle. Christian Huygens was a Dutch physicist who thought a lot about waves. In fact, he was the first one to propose that light would be waves, but Newton ruled in those days. And so he was not considered correct, but he was correct. Huygens says you treat each point on a wave crest as a source of expanding spherical waves, which then interfere to produce the propagating wave. It's kind of a complicated way to think about how a wave propagates, but it can be helpful. So on the left, I've got a picture of a straight wave, and you can imagine each point on the wave making these circular wave fronts, and they interfere a ways on, and that makes the later position of the wave front. If the wave front is circular, then you get an advanced and somewhat larger circular wavefront as the wave propagates outward. Well, that's not very useful, but it becomes very useful when waves interact with systems, particularly sharp edges and things that are small compared to the wavelength. So here's what happens, for example, at an edge. The waves bend as they go around the edge. Why do they bend? Well, look at the inset blow up here. You can see each of those wavefronts producing circular little wavelets. They're called Huygens wavelets. And normally in the middle of this region away from that edge, they're just going straight through. But right near the edge, there's no other waves to interfere, and you get this little bending around the edge. There's an analogy with sound. Low-pitched sounds whose wavelength is long compared to things like doors, for example, go around corners. High-pitched sounds whose wavelength is short don't show nearly as much of this diffraction effect. That's why you can be in your apartment or your dorm room or something, and there's some pounding bass from somebody's stereo far away, but you don't hear the high-pitched sound. That's diffraction at an edge. Here's a couple pictures of this. Here are water waves impinging on a barrier. The barrier is essentially made by those two little pieces of rock or island there, and you can see the diffraction, the circular wavefront spreading out beyond that barrier. Here's another example. This is a photograph of light waves diffracting at an edge. And you see the edges on the left where it's completely black, but instead of a sudden cutoff where it's either dark or light, you get these interference bands as the waves coming by the edge are interfering with each other as they go in slightly different directions. That's diffraction at an edge. Diffraction also takes place at apertures, any kind of hole that light might go through, slits, circular holes, the apertures of lenses for telescopes and mirrors, the large mirrors on astronomical telescopes. All these things are apertures, and you have to worry about diffraction effects on them. Here's what happens at an aperture. Here comes some incident light on a slit of some size. It's got now some finite size, which I'm going to call A. And you'll notice that what happens here in the inset is two waves that are half a slit width apart, two rays that are half a slit width apart, are going to interfere if that distance, A over 2, half the slit width, times sine theta, is an integer multiple of half a wavelength, and they will interfere destructively. So that's A over 2 sine theta is m lambda over 2, an integer multiple of a half a wavelength. That will give them destructive interference. Those 2's cancel, and we get destructive interference with this single aperture when a sine theta is m lambda. The first minimum in that pattern, place where m equals 1, then occurs when sine theta is lambda over a. What does all this mean? It means when I send light through an aperture, a circular aperture, a rectangular aperture like a slit, what will happen is I will get some interference patterns on the other side caused, as this little diagram shows, caused by the interference of light rays coming from different parts of the aperture. This takes into account the finite size of the aperture. And as you make the aperture smaller, you'll notice that angle gets bigger because sine theta is lambda over a, and that's where the first minimum is. So here are some diagrams that express that. Here's the case where a is 10 times lambda. So a is pretty big compared to the wavelength, and basically what you see for the intensity of light coming through the aperture is one big spike in the middle, which is what you would intuitively expect. But if you look closely, you see a couple little wiggles around there. Now we make a twice lambda, and you see something quite different. The pattern of light coming through the aperture has been spread out, and then it goes to 0. That's that first minimum, and then there's a small maximum, and it actually wiggles up and down for a while. And the point is, when the aperture gets small, you have trouble imaging the system as a single point of light, if in fact it was supposed to be a single point of light. And if you are trying to image some physical object, the image will begin to go out of focus. When the aperture size is comparable to the wavelength, the image has become spewed all over the place, and you've got problems. Diffraction prevents us from easily forming images. And let me give you some examples of that. The diffraction limit means we need very large apertures to resolve either closely spaced objects, like, for example, the planets in a distant solar system. That's why we have rarely got direct images of planets in distant solar systems. That and the fact that the stars are so bright is why we can't image most binary stars directly. This is called the diffraction limit. We need enormously large telescopes to overcome the diffraction limit. The other place where this becomes important is if we're trying to image very small objects with microscopy. We have basically the same issue. What happens is the two diffraction patterns, because we can't image a point as a point because of this diffraction effect, the two diffraction patterns overlap, and we begin to be unable to resolve things that are either too closely spaced, small objects, or too close in angle with large objects imaged by a telescope. And here's an example. Here's a system where we're trying to image a couple of objects, and they're far enough apart here that they look like a couple fuzzy blobs. You can see a couple of little rings around them. These are the diffraction patterns of the individual objects. As they move closer together, those diffraction patterns get a little closer together. Now the diffraction patterns are beginning to merge, and these objects, which should look like points of light, but aren't because of diffraction, begin to become indistinguishable. There are still two objects, and you can just barely see the thing is slightly elongated in the vertical direction, but diffraction has wiped out our ability to resolve them. And finally, they're sitting just about right on top of each other, and we can't even tell that there are two objects there. That's the diffraction limit. Diffraction limit is a serious limitation that the wave nature of light places on our ability to image things. By the way, one way around this is to use shorter wavelengths of light. That's one reason people doing microscopy, biologists and so on, will move to ultraviolet wavelengths or electron microscopes where you can control the wavelength associated with an electron. More on that when we get to quantum physics. You don't have that option when you're doing astronomy, for example, and you need to observe at a particular wavelength of light. Diffraction limit really prevents us from imaging very small or very closely spaced objects. How can we get around it? Well, we could, as I mentioned, lower the wavelength. That's why we use UV and electron microscopy. That's also what the difference is between a Blu-ray disc, a DVD, and a CD. CDs can hold about 700 megabytes of information, 0.7 gigabytes. DVDs can hold just under 5 gigabytes. Blu-ray discs can hold about 25 gigabytes. Now, there are a number of technological differences, but the big difference is the color of the laser used to image the information on that disc. And in the case of Blu-ray, the laser is blue, and it has a roughly 400 nanometer wavelength. These pictures are all at the same scale. It's about 4 micrometers vertically on those pictures. And the spot, because of diffraction with the red laser, is simply bigger. And so the information-containing structures, which are these little pits, have to be bigger. And so a major part of the reason why Blu-ray discs hold so much more is because of the invention of a simple, inexpensive diode laser that could produce blue light, hence the name Blu-ray. And we're getting around the diffraction limit. We're able to image smaller structures or to get information from these smaller structures. And finally, in astronomy, you achieve the same effect by using larger apertures. And radio astronomers are particularly good at this because they will take a whole bunch of radio telescopes, spaced perhaps widely apart, in one case spaced all around the planet. And they basically simulate a single telescope with an aperture that big. And so they can do very, very exquisitely precise measurements and imaging with radio astronomy using these enormous so-called interferometric telescopes. It's much harder to do with optics, but it can be done. Okay, well, let's wrap up. We've seen that the wave nature of light becomes significant when light interacts with objects comparable in size to the wavelength, and interference is at the heart of what's going on with these wave phenomena. We've seen thin film interference, interference in slit systems, with diffraction grating and spectroscopy, diffraction at edges, diffraction when light passes through apertures, and this diffraction limit, limiting our ability to image objects of small size or small angular separation. So that's it for optics, but before you go, if you're interested in a challenge, here's a challenge for you. That picture I showed you before of the soap film, how thick is the soap film in the black area at the top of the film? The shortest visible wavelength is about 350 nanometers, and the refractive index of water is 1.33. Work it out, I'll come back with the solution. Here's the solution. We get constructive interference when twice the thickness is m plus a half lambda as measured in the medium, in the soap film, which is made of water. The lowest d will occur when m is 0. In that case, I have m being 0 and I have 2d equals a half lambda in the medium. The twos come together, become a 4, and d is n lambda, lambda in the medium, divided by 4. That's lambda divided by 4 times the index of refraction, where lambda is now the wavelength in air, not in the soap film, and that's 350 nanometers divided by 4 times the index of refraction, 1.33, and that's 66 nanometers, 66 billionths of a meter, and you've measured it. That's the thickness right where that soap film becomes black or becomes transparent because no light is reflecting off it. No interference pattern can be met, no interference condition can be met for visible light.